In this module, we're going to see a little bit about the regression basics. Specifically, we're going to focus on the least squares estimates. In regression, the variable y is called the dependent or the response variable. And we are interested in estimating its true mean, or what we call the expected value of y. Generally, for example, if we have a variable like sales that we want to estimate, the most common way to estimate it is just to get the mean of the sales. And that is a valid estimate. That's what we use when we generally estimate it using univariate statistics. But in regression, we are interested in estimating the y variable, which is a numeric variable, using other predictors. So the expected value is going to be based on other variables, such as, in this example, the date. Maybe sometimes if it is, let's say, a weekend, we can have higher sales than if it were other days of the week. Maybe we are interested in estimating the sales using other predictors, such as the advertising expenses that we put in that product, or other predictors. So, in other words, in regression, we are interested in estimating the y variable, but we are basically using predictors, or just single predictor or multiple predictors, to get that estimate. In every estimation, there is what we call an error, and this is a random error in regression. What that means is that it is not estimable. We can't predict it. So basically, to summarize, the expected value is what we are interested in getting the estimates for. And it can be a function of one variable, or it can be a function of multiple variables, like, for example, the advertising expenses, the sales the previous month, economic variables, economic conditions. So that expected value is going to be a function of one or more variables. In regression, we generally use observational or experimental data. Observational data means that in the regression, the variables are measured by just observing their values. Okay? Whereas in experimental data, the values of the independent variables are controlled using some sort of designed experiment. In that case, we call it experimental data. For this course, we're generally going to use observational data, which means that we have data, we have gathered somehow the data, and we have observed them from history. Let's say if we have, as we are estimating the variable sales, that's the history of the sales that we have seen for that particular product. But we are not interested in looking at experimental data, but that is also a valid area. A first order model is one that looks like the equation that you see right here, where y is the dependent variable, the variable to be modeled, to be estimated, or the response variables, we call it as well. X is an independent variable, so this is just a single variable regression, which we call simple linear regression. And the expected value is going to be modeled by a straight line. In other words, we have a y-intercept and a slope. The error component, epsilon, is a random error, which means, like I mentioned before, that it is not predictable. The beta 0 is a parameter, which means it's a value that is based on a population. So is the y-intercept, and that's what we are interested in estimating. The way that the slope and the y-intercept are defined in statistics is similar to the way that it is defined in mathematics as well. The slope is just the rise over the run, and the y-intercept is the point where the value of x is equal to 0. Now, the only difference here is that in regression, we have some error, which doesn't happen in a regular linear equation in mathematics. So in other words, beta 0 and beta 1 are, again, the parameters. Beta 0 is the y-intercept, and beta 1 is the slope. We don't know the true values of these parameters, so we have to have sample data to estimate them. So we are going to call these estimates beta 0 hat, or B0, or we can call beta 1 hat, or B1, to estimate beta 1. So the estimated equation is a way to get the estimates of that expected value of y, the average y. And that's what we are interested in doing here in regression. There's going to be errors. So in other words, whenever we have an estimate in the equation, there's not going to be, the points are not going to lie exactly on the prediction. In other words, there's going to be what we call an error of prediction, which is going to be the difference between the actual value y and the predicted value y hat. Okay, let me give you a quick example. Suppose you're trying to predict the sales, and this is in thousands of dollars, and these are the values that you have observed in the past, observational data. You're using expenditures in hundreds of dollars to get estimates of the sales. So in other words, if you have these values right here, then the first thing you want to do is basically plot the data using advertising expenditure, the X predictor variable in the X scale, and sales revenue in the Y scale. You're trying to get the estimates of the sales revenue, and those estimates are obtained if we get some sort of line. The line is defined by both a slope and a y-intercept. In other words, it might be something like that. The slope is just how much the rise over the run. And then the y-intercept is going to be the place where it hits the y-axis when x is equal to 0. These are obtained generally with software. Software like R, like SPSS, like SAS, like Minitab, like Jump. And in this course, we're going to use R to get those estimates. The estimates are called the least squares estimates, and we will see why that's later. In this case, the computer found that the estimates are the y-intercept to be minus 0.1, while the slope is estimated to be at 0.7. We're going to take a look more at how we get those parameter estimates. But first, what we want to do is show you what is the predicted values. The predicted value is plugging in the y-intercept, the estimate, and the slope, and then basically solving for the value of y. In other words, when x is equal to 1, if we plug 1 to this equation, then we're going to get an estimated or predicted value of 0.6. But there's a difference between the actual and the predicted. That's what we call the residual error. The error in the first observation is 0.4. In other words, the actual minus the predicted is 0.4. If we see the other observations, we can see that there is a negative error and there's a positive error. But there's always going to be the condition that if you sum those up, it's going to be 0. If you sum the residual errors, that's going to be 0. Sometimes we're interested in looking at the squared error. In other words, the sum of the squared prediction, the squared errors of the prediction. So we get this value and square it, and that's what we call the squared error. If we sum the squared errors, we get the SSE value, the sum of the squared errors. That's going to be a very important statistic for us. The sum of the squared errors is something that we want to minimize. We want to get it as low as possible. The lowest could be is 0, but because these equations are going to always have some sort of error, then generally we can't get it as close, can't get it to 0. We want to get it as close as possible. Okay, so what is the method of least squares? Is the method of estimating beta 0 and beta 1 by minimizing the value of SSE. In your notes, you have a derivation of how this is obtained, and you don't need to remember this for exams or anything like that, but we wanted to show that to you so that you can see where these estimates come from. Mathematically, these estimates come from by taking the minimum value of SSE. The minimum value of SSE can be obtained by using derivatives. If you take the derivative of SSE with respect to the variables that you're trying to estimate, which are the beta 0 and beta 1, you get those equations right here. If you set them to 0 and you solve for beta 0 and for beta 1 and those equations, then you are getting the minimum, the value of beta 0 and beta 1 that get the minimum SSE, which are these values. Again, in your notes, you have the full derivations right there. Not that you need to remember those or commit those to memory, but it's important to know what the method of least squares is. This is the method that gets the least squares errors. In other words, the least SSE.